All right. So we're going to continue talking about chi-squared. Just a really quick review. Chi-squared is a test for independence that compares two quantities using a two-way or a contingency table. Now, let's go ahead and practice. There's one thing, the original data that you collect is called the observed data. And then we want to go ahead and, in order to calculate our calculated chi-squared value, we go ahead and find what's called the expected frequency values. So the expected values are what we would expect to get if the two quantities were independent. There was no relationship between them at all. And that's primarily, why we have this test for independence. When comparing the two quantities, is there any association between them? Is one dependent on the other, or is there no association at all? They are independent. The good news is it'll tell you that, basically yes or no, depending on our critical value that we're given. But it doesn't tell you the nature of the relationship. So you'll have to go ahead and infer what you believe the relationship is. How does one actually depend on the other? Okay, so let's go ahead and run back to one of these. As far as the expected frequency, okay. And these were some examples we were looking at last week. Let's say for this example right here, comparing level of school, whether it's junior, middle, or high school, to playing or not playing a sport. So let's say I wanted to go ahead and find the expected frequency value for a junior school student who plays a sport. So this right here. Does anybody remember how we find that expected value?
The total at the bottom.
Okay, so we take the column total, 58, times the row total. See, we want to go ahead and find the cell that they intersect in. So we're going to multiply 58 times 165, and then we divide by what? There you go. If you take a look at the bottom right corner right here, we know that there were 250 people in this particular survey. So you always divide that product by the total number of people. So in this case right here, 58 times 165. Let me get on over here, calculate. Okay, so 58 times 165, and then we're going to divide that by 250. Okay, it's going to go ahead and give me my fractional value. Okay, so I'm looking at about, oh, it did not give me what I needed. 957 divided by 25. Let's do that. Okay, control enter. There we go. So we're looking at about 38.28 would be the expected value. 38.28. And then you would do the same thing for each of the other observed values that you collected. So is everybody okay with the expected frequency values? Okay. And then the other day we got to this point where we talked about, okay, what's the value, the critical value? How do we go ahead and determine it so that we know by what point the value of our calculated chi-squared test is either too large or too small? What do we go ahead and compare it against? Well, you go ahead and talk about what's known as the degrees of freedom and the significance level. Now, the significance level is the level at which you're going to test these two quantities. It's typically 1%, 5%, and 10%. Now, the degrees of freedom, that's going to be the number of columns from your contingency table, minus 1, times the number of rows from the table, minus 1. Okay? Do we need to kind of revisit the degrees of freedom, or do we still remember what that refers to from last week?
That's like the number of columns minus 1 times the rows.
Yes. Now, specifically the degrees of freedom, let's say we got this contingency table here. Well, because we have 2 columns and 2 rows, this would be 2 minus 1 times 2 minus 1. So the degree of freedom right here would be 1. That means that any of these 4 cells here, I could choose any value that I want to go ahead and input, as long as it works with the totals that I have. So for example, let's say right here, I go ahead and put a 6. I could choose to put any number there, but because this has a degree of freedom of 1, I now no longer have a choice. Okay, I know that in order to get this 12 right here, this one has to be a 6. See, I can't choose that anymore. Same thing here, I know that 6 plus what will give me 15? 9, right? Okay, and then what would this be right here? Oh wait, did I mess up?
Something's not right.
Did you start with...
Yeah, I started with a good value because 6 is less than 15 and 12. Ooh, that's interesting. I've never seen that happen. Let's try that again. maybe a 5 and a 7, and then that would be, holy cow. That's interesting. I gotta look into
Are
that.
their values accurate?
I wonder if their values are accurate, yeah. Okay, but regardless, does everybody get the idea? Okay, you get one cell that you can choose the value, but then the others have to go ahead and depend on that value you chose. And I think this is about where we got to last week. Here's a 3x3 where the degrees of freedom are going to be 4, so I could choose 4 values, 4 cells to be whatever they want to be, whatever I want them to be. But then after that, starting with the 5th cell, it's going to depend on the values that I've chosen. It's no longer my choice. Okay. Now, once you have the degrees of freedom, and then you go ahead and get yourself the test at which you're performing this at, whether 1%, 5%, or 10%, then you use this table right here to go ahead and determine what your critical value is. This is what you're going to compare your calculated value to. Now remember, we've already calculated several of these by hand. We got one that was very small, I want to say like 0.217, and then we got one that was much larger, which was 6. So whatever we calculate from the table, or even on the calculator, that's what we go ahead and compare to our critical value. Okay? Now, very important, in order for chi-squared to be distributed appropriately, the sample size n must be sufficiently large. Generally, n is sufficiently large if no values in the expected value table are less than 5. Now, there are a few restrictions when it comes to chi-squared tests for independence. One of them being, if you have expected values that are less than 5. Let's come back over here, like maybe to one of these. Okay. If any of your expected values turn out to be less than 5, that could potentially be a problem for your results. But as long as no more than 20% of your cells are less than 5, your results should still be valid. I did talk to Mr. Reeves about that. Okay, so it is a problem if any of your expected values are less than 5, but if overall no more than 20% of your cells are less than 5, you should still be okay. There is also another issue with certain contingency tables, like this one that I was just showing you a moment ago. Okay, like this one right here. If the degrees of freedom are actually 1, there is potentially a problem with your results. You're going to have to use what's called Yates continuity correction. I don't think I'm actually going to go ahead and teach that in class, but I will post videos about that. So if you do come across it, maybe in your IA, you can have this as a reference, and you definitely always talk to me about that. Okay, I just wanted to go ahead and bring that up right there. Okay, so what does all this mean? The p-value. When finding chi-squared on a calculator, the p-value is also provided. This can be used together with the chi-squared value and the critical value to determine whether or not to accept that the variables are independent. So you're going to make your decision by comparing our calculated chi-squared value to the critical chi-squared value. Depending on if it's larger or smaller, we're going to go ahead and say, yes, there's an association, or no, there is not an association. The p-value, kind of think about this as a confirmation, as a way of double checking the original conclusion that you made. So the p-value could very well agree with your original assessment, or it could actually contradict what you have. Now, normally in years past, I hadn't spent a lot of time on the p-value because we simply compare the chi-squared calculated to the critical value. But the last time we had paper exams, not this past one because back in May, they were, of course, canceled due to COVID, but the year before that, they actually had a problem on one of the paper exams where you were not provided a critical value. They did not provide the table, but you could still solve the problem using the p-value. Okay, so that is definitely something we want to go ahead and keep in mind, and I'll show you what I mean as soon as we get to an example. Okay, so for a given contingency table, the p-value is the probability of obtaining observed values as far or further from the expected values, assuming the variables are independent. Okay, I know that a lot of this stuff doesn't make sense right now, but just kind of hang in there with me. When we get to an example, I'm going to help you out. If the p-value is smaller than the significance level. Now again, when you hear that phrase significance level, that's the level at which we're testing our hypothesis. Remember, that's the 1%, the 5%, or the 10%, whatever's been chosen. So if the p-value is smaller than the significance level, then it is sufficiently unlikely that we would have obtained the observed results if the variables had been independent. We therefore conclude that the variables are not independent. That means there's some type of association. There is some type of relationship with them. Okay? They're not independent of each other, they are dependent in some way. Now, it's not always essential to use the p-value when testing for independence, as we can perform the test by simply comparing the calculated to the critical. However, the p-value does give a more meaningful measure of how likely it is that the variables are independent. So like I said, we're going to use it as kind of a way of double checking ourselves. Okay. So here we go. Here are the steps for the test for independence. We state H naught, okay, that's the null hypothesis. This is a statement that the two variables being considered are independent. That means there's no association. Okay. State H sub 1, that's the alternative hypothesis. This is a statement that the two variables being considered are not independent. We have an association. State the rejection inequality, so the chi-squared calculated value you get greater than k, where k is the critical value. Construct the expected frequency table, use technology to find our chi-squared calculated value. We either reject the null hypothesis or do not reject the null hypothesis, depending on the result of the rejection inequality. Now here's something really important. This guy's helping us out here. It says we write we do not reject rather than we accept H naught, because if we perform the test again with a different level, we could end up with a different result. Like if I go ahead and perform a test at 10%, it could say that there is a relationship between the two quantities. But if I perform the same test again at 1%, it might decide that now there's no relationship. So that's why we go ahead and word this the way we do. So we either reject or we do not reject the null hypothesis. Okay? Very similar to what we were doing with the t-test. Okay. We could use a p-value to help us with our decision making, and here it's written out just like this. Okay? So if the p-value is less than your significance level, we reject the null hypothesis. That means the alternative hypothesis must be true. If the p-value is greater than the significance level, we do not reject the null hypothesis. Okay, so that means they're got to be independent of each other. There's no relationship, no association. So I know this is a lot of information coming your way, but let's go ahead and try a problem. A survey was given to randomly chosen high school students from years 9 to 12 on possible changes to the school's canteen. Do you know what I'm referring to when I say canteen? We're talking about the school cafeteria. Okay. Now, the contingency table shows the results at a 5% significance level. Test whether the student's canteen preference depends on the year group. Okay. So we've got our null and our alternative hypotheses. Okay. Now, this is the first time that we're not going to do this by hand. I'm just going to walk you through the entire thing on the table, on the calculator, that is. But let's go ahead and write our null and alternative hypotheses first. So we're comparing year group to the school's canteen, right? The null hypothesis is always going to state that the two quantities are independent. So I could go ahead and say something to this effect, that the school's canteen and what is it, year group, if I could write today, that'd be fantastic, are independent. I'd probably go ahead and say are independent of one another, but I'm just going to go ahead and say are independent. So what do you think the one change is going to be for the alternative hypothesis? There you go. Remember, the null hypothesis will always state that the two quantities are independent. The alternative hypothesis will state that the two quantities are not independent, meaning there is some kind of relationship. So I'm going to say the school's canteen and year group are not independent. And you could even just go ahead and say are dependent. That would be just as fine. Okay. All right. So let's go ahead and finish this contingency table right here. So we've got the different years, freshman, sophomore, junior, senior. So we have the year group, and then we're going to change the cafeteria, or we're not going to change the cafeteria. So let's go ahead and see if we can determine how many students total were in the survey. Let me go ahead and get rid of that hand right there. Oop, he came back. Okay. So we're going to go ahead and leave that hand right there. It's not a big problem. There we go. Okay. So let's go ahead and start to add these up. Like, for example, what is 7 plus 14? 21. So I know there are 21 freshmen total. And let's just continue to add up the columns here. So I have 9 plus 12. 21. What about 13 plus 9? 22. And then 14 plus 7, once again, will give me 21. So now let's go ahead and add this up. 21 plus 21 plus 22 plus 21. Okay, that's going to give me 85. Would everybody agree? Now let's see if it matches up when we look at this by the rows. So I need 7 plus 9 plus 13 plus 14.
43.
I'm getting 43. 7 plus 9 plus 13 plus 14 would be 43. And let's add 14 plus 12 plus 9 plus 7. I'm getting 42. Is that what you guys are getting? And let's see. What is 43 plus 42? It is giving me 85. Okay, so we have that. We're good. Now, here's the thing. We could go ahead and plug this in the calculator. We're not going to find this by hand. If you do want to go ahead and determine it by hand, we can absolutely do so. We can even connect it to the calculator if you'd like. But we need to go ahead and put this data, the observed data, into the calculator. Okay, so how are we going to do that? Sorry, man. We still got time? Oh, yeah, we got plenty of time to do this. Okay. So what size matrix is that? How many rows by how many columns?
2 rows.
2 rows by 4 columns. So this is a 2 by 4. So if you're going to put your observed data into the calculator, you need to go ahead and put it in as a matrix. Okay, so I'm going to come on over here. Okay. I'm going to come to my home screen. Let me go ahead and clear this off. Okay. So document B. It did not take it. So let me delete that. Document B. There we go. So if you go right here, if you'll notice, this button right here between 9 and the open book on the right side middle of your calculator, it's this button right here, right below delete, next to that open book. If you go ahead and push it, it's going to bring up a whole table of icons where in the middle we have a lot of matrices. Here's a 2 by 2, here's a 1 by 2, 2 by 1. We want to go ahead and click on this 3 by 3 here. This is the only one that allows me to go ahead and change the number of rows and the number of columns. Okay, so we're going to go ahead and say there are 2 rows by 4 columns. Now, did everybody happen to see that? Does anybody need me to go back and show you where that was? Okay, so I've got 2 by 4 in, and see, it's going to go ahead and give me a blank 2 by 4. So now let's go ahead and put in all those values. I don't have the data in front of me. Can someone tell me what the top row was? 7. 9, and I'm using my arrow key to go ahead and get to the next one. 13. 14? Okay. And I'm going to come down here. 14, 12, 9, 7. Okay, so once you put in all of your observed values, you want to arrow out of the matrix. Okay. Now, we need to go ahead and manipulate the matrix. We need to go ahead and name it. So once you arrow out of the matrix, you're going to push your control button right here, the blue control button, and then you're going to hit this variable button right above 9, because we're going to store it in the calculator's memory as whatever we want to call it. Typically, I like to go ahead and call it like matrix X or Y. Okay. So you hit control, variable, and then you can title it whatever you want. So when I push enter, the calculator now knows this 2 by 4 matrix is X. So see, if I go ahead and just type in X and I push enter, it's going to go ahead and bring up that same matrix. Okay. Now, what we want to do, let's go down here to menu. We're going to go to statistics, stat tests, and you'll notice we want the chi-squared two-way test. This is the test for independence. Remember, two-way refers to a contingency table. We don't want GOF yet. That's goodness of fit. We're going to do that later. Okay, so let me get back out of here again. So once you have your matrix data in the calculator, I went to Menu, Statistics. Okay, we're going to go to Stat Tests, chi-squared two-way test. Okay, and it's going to say what matrix do you want to go ahead and use as your data. Well, this is where I'm going to type in X, or whatever it was you chose to name it. Then I'm going to go ahead and click OK. And here we go. Here's my chi-squared value. There's the p-value. It even tells me the degrees of freedom, right? Okay. Now let's say that your problem wants to go ahead and ask you about the expected frequency matrix. Now we're going to go ahead and finish up the problem in just a second, but if you were to go ahead and do this, once you have your results, if you click on this button right here without hitting Control, the variable button that you did to store it, click on variable, and you'll notice, look for EXP matrix. This will give you the expected value. So when I click on it, okay, push enter, there's the expected values we would get if we multiplied the column total by the row total and divided by the 85 total sample people that we had in this survey. Okay, and we can double check those if we want to. But let's go ahead and see what we got here. My chi-squared value, let's say, is 5.81. Okay, it's 5.81. So I'm going to come back over here. Okay, 5.81. Now, we need to know what our critical value is. That wasn't given to me. What were the degrees of freedom?
3.
Okay, if I look at the calculator, the degrees of freedom are 3. And remember, we're testing this at what level? 5%. So I'm going to come back over here to this table that I was given to you in our notes. So we have degrees of freedom of 3, and we're testing it at a 5% significance level. So we want to go ahead and find the value that intersects the two. It looks like my critical value I'm going to compare to is 7.81. So I'm going to come on over here. Okay, whoops. 7.81. Now, our calculated value is actually less than 7.81. So let's see what this actually means. Okay. What am I going to say here? Am I going to go ahead and reject the null hypothesis? Or am I going to not reject the null hypothesis?
Reject.
Okay. Now, if you're not sure from here, maybe we go back one more and take a look at this. Oh, that's the p-value. Okay. Where was the slide where it talked about this? Oh, I actually have it on the same one down here. I just wrote it out myself. I can't believe I forgot about that. Okay. So if your calculated value is less than the critical, they're independent. We accept the null hypothesis, or we do not reject it. If your calculated value is greater than the critical, then they're not independent. There has to be a relationship, okay? And we reject the null hypothesis. So we saw this scenario right here. We saw that our calculated was less than the critical, so that tells me they have to be independent. There's no association, okay? So what we're going to say, instead of accepting the null hypothesis, we're going to say we fail to reject, or we do not reject. So based on this, there is no relationship between the classification of a student by year group and anybody wanting to change anything in the cafeteria. Okay? But let's go ahead and confirm this, because remember, there was one other way to do this. What was our p-value? Let's say 0.121. I'm going to take my p-value of 0.121. Okay? And remember, we're testing that it's 5%, so 0.05. So what's larger? 0.121 or 0.05? Okay, so that's greater than. Now, it is on this other slide right here. Okay? If the p-value is greater than your significance level, we do not reject the null hypothesis. Well, what statement did we or what conclusion did we come to here? Did we reject the null hypothesis? We did not. So this is actually confirming what we got is correct. Now, I will go ahead and say that if comparing the p-value to your significance level, if it does contradict what the original conclusion said, go with this. Go with what the p-value is saying. Okay? That's the more exact way of testing these. Okay. And there we go. That is the chi-squared test for independence. How are we doing? I know it seems like a lot, but remember, this is the first time we've seen one of these problems on the calculator. The next time we'll go a little faster because we'll already know what to expect. Okay. How are we doing at home? Does anybody have any questions? All right, so we're going to go ahead and stop there for today because we did have a survey we were going to have you guys fill out very quickly.